Did you know that the most precise clocks don't lose or gain a second in 30 billion years? That's more than twice the age of the universe. Here at ISOLDE, a nuclear physics facility at CERN, we have just taken a step forward towards building a nuclear clock that could run even much more precisely. We have observed a transition in thorium-229 which could make a nuclear clock tick forward. So, how did we do this? ISOLDE directs a high-energy beam of protons from CERN's proton synchrotron booster into specially developed targets. This generates a large variety of radioactive atomic nuclei, those with too many or too few neutrons to be stable. Different devices are used to ionize, extract, and separate the nuclei according to their mass. The nuclei are then delivered via beamlines to many experiments. In our experiment, we incorporate actinium-229 nuclei into the crystalline structure of a magnesium fluoride crystal. In the crystal, the actinium-229 nuclei transform into thorium-229 through the emission of an electron. This leaves the thorium-229 nuclei in an excited state, called an isomeric state, that then decays emitting light that is detected by a spectrometer. This is the transition on which a thorium-229 nuclear clock would be based. We have used the wavelength of the observed light to measure the excitation energy of the isomer 7 times more precisely than previous measurements. This will help people to develop a laser that can make the nuclear clock tick forward. So why is such a nuclear clock actually interesting? Well, if we take this nuclear clock and we compare it to the best available atomic clock, we might see a slight shift in their ticking frequency. And then we might ask, where does this come from? Well, actually, fundamental constants of nature might not be so constant in time, or there might be the presence of ultralight dark matter. With this study, we have actually shown that we can go a big step forward towards the realization of a nuclear clock that can study all these effects.